Hello and welcome to Microfile, a chance to see again some of the best items from the MicroLive series. This week we look at some of the research which will influence future generations of computers. Now, most computers in use today have similar architecture and they use the same electronic building blocks. But tonight we look at some of the alternatives.
First, let's examine what one of the fathers of modern computing, Alan Turing, thought were the fundamental features of a computer. This is a clip from the West End stage play about Turing's life, called Breaking the Code. Many of the speeches in it were based on Turing's radio broadcasts of the 50s, and we join the play as he describes to his old school what a...
And the logic of a computer is really very simple. All it does is to read a list of instructions and then carries it out methodically. And the only thing you have to do is to write down exactly what you want done in a language the computer understands. This is what we call a program.
Well, computers have certainly come a long way since Turing's day. Current technology products include work on something called fifth-generation computers. But what exactly were the other four? The demarcations are rather hazy, but there have been definite hardware developments, computer milestones if you like, and alongside those, but not necessarily in step, there's also been developments in programming languages. Now, those early first-generation computers were huge, great machines. They were packed full of thousands of valves, and they could only be programmed in machine code using the ones and zeros or ons and offs, which to this day are the only things that digital hardware can understand. Here's the world's first computer program, which would have been entered via a punched paper tape, and you needed to be a mathematician or an engineer to work with it.
The smaller, so-called second-generation machines appeared in the 1960s, and they were a direct result of the invention of the transistor. They were, of course, more reliable, and second-generation languages like assembler were increasingly being used. Now, assembler or assembly language is a set of mnemonics which help a programmer to enter machine code. For example, the machine code to store a number in a part of memory called the accumulator just happens to be 169. But in mnemonics, it becomes LDA, load accumulator. Very much easier to understand.
But it is still not a piece of cake exactly. One line of assembly code generates only one machine code instruction, which means that any task at all needs to be broken down into endless small steps. In contrast, one line of a high-level programming language like Fortran generates anything up to 100 machine code instructions. And by the 1960s, this was the sort of language being used by software writers who found it faster because it was easier to use and easier to understand. I mean, you get good English words, things like if, go to is certainly understandable, write and format, and so on. Now, these are third-generation languages, but they were running on second-generation machines. It wasn't until the late 70s and the development of the chip that the hardware caught up and microtechnology became known as the third generation.
This progression towards a more natural human language continues. With this fourth-generation language, Informix, it's possible to write a database application in just a few minutes, whereas, of course, with a third-generation language like, say, COBOL, it might take several weeks. I'm preparing a database about company cars. Now, so far, I've only defined what information each index card is going to hold. But now I need a program to allow me to search through those cards and to add or retrieve information. Well, in this language, I can enter keywords like this one, form build, if I can spell it right. Yes, there we are. And that will generate the program for me. Now, what do? I enter the name for the form. I'll call that V for vehicle, and the name of the database, C for cars. Now it tells me it will be compiled. It's compiled for me, and it's been completed successfully already. Now it runs, and it's produced a blank index card. I can now enter the details for those cars, the owners, and so on. So this is an applications generator. It's a typical fourth-generation language. But what on earth is a fourth-generation machine? Basically, it's little more than advertisers' hype. The development of VLSI, very large-scale integration, has enabled a complete computer to be built on a single chip. As for instance, there are something like 60 just here. Now, it's arguable whether this represents a whole new generation of machines. The title fourth generation was forced on the world when the Japanese announced that they were working on the fifth.
Yes, the Japanese government has encouraged Japanese industry to invest heavily in fifth-generation research. They have very specific requirements too. They want machines that respond to the kind of language that we use every day, that learn and reason for themselves, and also there's a lot of interest in robots that can see and can interpret what they see. So, where is our future research in this area going to come from? In Britain, the first ALVI research programme is currently being wound up. And only this week, European ministers failed to agree on any more funding for fifth-generation research and development as the British were dragging their heels. But there is one institute here that was set up a few years ago. It's named after Alan Turing, and it pays for its own research by selling its expertise worldwide.
And so the name of Turing lives on, and the fate of future public funding is still in the hands of various parliamentary subcommittees.
Fifth-generation machines are still using electronic switches to process information. But there may come a time when electronic computers just aren't fast enough. Fred visited Heriot-Watt University.
Now, the microprocessor is an immensely complex piece of electronic design, but behind that complexity is a very simple principle. The basic building blocks required to make any modern computer are always the same, and those building blocks are no more than simple decision makers or electronic gates. This AND gate, for example, has just two inputs here and here and one output. Now, each of these inputs and outputs can be in one of two states. Either the lights are on or off. The state of the output here depends on both of these inputs being high, in other words, the lights being on. So this will be on only if that and that are on. In other words, it's an AND gate. One alone is not enough, both together will light the output. When simple gates like this are connected together in very large numbers, you can start to build up the very complex functions you expect from, say, a modern microprocessor. Now, a microprocessor is small, it's very cheap, reliable, and it's fast. But for an increasing number of applications, it's proving to be just not fast enough. Artificial intelligence work, Star Wars research, visual recognition systems are all making demands which the modern microprocessor and the modern computer will find it impossible to meet. Now, the problem is a fundamental one, and it's because all computers are built from electronics.
It's not possible in electronics to communicate information from one switch to another infinitely quickly. The reason for this is that they are circuits, and the speed of transfer of information in these circuits doesn't get smaller as the circuits get smaller. So that even if you make extremely fast transistors, you may be unable to transfer the information to the next one as quickly as they can switch.
So, as far as speed goes, electronics is a dead end.
In the end, electronics will reach a limit. It'll reach a communications brick wall, in fact.
So, what's the answer?
Well, the solution, we think, may lie in optics.
So here at Heriot-Watt University near Edinburgh, they've been working on what some people rather inaccurately call the world's first optical computer. Using a large industrial laser and a maze of lenses, prisms, filters and holograms, Desmond Smith and his team have reached an early landmark in what promises to be an important new technology.
We have to reinvent the triode valve from 1907. Essentially what the triode valve did was provide a means by which electricity could control electricity and thus provide a very fast switch with no moving parts. And that, of course, is the basis of electronics, later transferred to solid-state electronics in transistors and then integrated circuits. So we've had to essentially create an optical transistor. That's to say, a small device in which a quite weak light beam, albeit these days from a laser, can actually control another light beam and give exactly the same effect that the triode valve gave. That is, an all-optical switch plus the other attribute of the triode, which is gain.
Well, the switch in this case is this tiny optical filter, but it's one with very unusual properties. We're firing a laser beam down here through the filter, and I can control the intensity of the beam just here. Now, as I increase the intensity, you'll notice there's very little increase in the output here, until, that is, I reach a critical stage when suddenly, there you are, it leaps high. Well, that's our high output, our high state, and you'll notice that the system acts as if it's got a memory, because as I pull back the intensity, it stays high until I reach another critical point and down it goes. Well, that's with me controlling the beam, but I can use light to control it. We've got a second laser coming in just here, and just flicking that in as a trigger switch will switch the output high. There it goes. Now that is very much the way a transistor works. except that with a transistor you've got electricity controlling electricity. Here you've got light controlling light.
I haven't yet explained why we think that light can actually, in the end, produce some advantages over electronics. And the reason for this is that we can use the parallelism which is natural in optics. A lens, which we've got in our eyes, and when we look at each other, can resolve at least 1 million spots. If one has small devices in which light can control light, then this lens can effectively constitute 1 million wires. And that wiring possibility, in parallel, is what gives us new possibilities for computer architecture. And if we are able to do optical switches only at the same speed as electronic switches, but multiply them by a very large amount of parallelism, might be 10,000 or 1 million times, then the overall speed of processing information could indeed be very high.
Try crossing 2 tracks on a printed circuit board and you've got a short circuit. But you can safely cross 2 or more beams of light and they won't interfere with each other. Now the upshot of this is you can split a single beam into many thousands of separate parts, doesn't matter if they cross, and each of them can be processed separately. Here, a hologram splits a single beam into 25 parallel beams, and each is being controlled independently. Which may not look impressive, but it is a form of parallel processing, and that's what the research here is all about. So far, the most complicated circuit they've achieved is this: 3 separate switches that operate one after another.
We've been able to make, therefore, the first optical circuits. One device will drive another, and then a third, and then back again to the first. That is essentially a very, very primitive computational loop.
Well, it's taken 80 years to develop electronic computers. Will it take another 80 to develop optical ones?
Well, I don't think it'll take 80 years. I think we shall see some devices within 10 years, but I don't think we shall see a general-purpose computer within 10 years. Rather, we shall see something for some special purposes. For example, if you want to do pattern recognition, what you would like to do is to access a series of memories, not one part at a time, as conventional computing does, but in parallel, so that you could actually compare a whole series of patterns to the one you're trying to recognize very quickly. It is that sort of thing that we may see a specialized device somewhere in the middle of an electronic device within the next 10 years.
Optical computers are obviously a thing of the future, but one way of speeding up the present technology is to take a new look at the heart of the machine, the microprocessor. Every microprocessor has a set of instructions it can obey, but some of those instructions are used more often than others. Here at Stanford University in California, John Hennessy has produced a chip with a reduced set of instructions, a RISC chip.
The basic idea behind RISC is to try and increase computer performance by trying to concentrate on the most frequently executed instructions and to increase the performance of the entire application by making those instructions run faster. Each instruction must justify its existence by actually showing how it contributes to improved performance. The instructions that tend to get dropped are more complicated ones. For example, the VAX has an instruction which does polynomial evaluation. That's an instruction which is so infrequently used that its benefits are virtually non-existent. This actually brings up one of the sort of fallacies about RISC. People say, well, you take this machine and you take out something, so therefore I've really lost something. And the analogy I like to use is one of a racer, an athlete who's running a race. Clearly, if he reduces and loses some weight, you haven't lost something, you've actually gained something. And what we try and do in designing RISC machines is to use the excess silicon area that we've recovered. We've actually gotten back. It's no longer wasted. We've recovered it. We use it for something that will really improve performance.
All the straightforward, simple instructions remain, and the more complex ones are broken down into 2 or more simple instructions which then run faster.
I think if you were to say what idea is most common to all the RISC machines that have been done, the idea of single-cycle execution is probably the most predominant concept.
Every chip has an internal clock which ticks millions of times a second. A standard chip could take several ticks or clock cycles to complete one instruction. But a RISC chip executes its simpler instructions much faster, averaging little more than a single cycle per instruction.
One of the key concepts in hardware design is the notion of pipelining, which is very much like the concept of an assembly line in a factory.
Several jobs are being done at once in rhythm. And just as a new car is begun at regular intervals, so the chip aims to start a new instruction at each tick of its internal clock.
One of the ways that we try and do that is by scheduling the pipeline in software and actually trying to keep the pipeline working at a very rhythmic rate so that we get tick, 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 one instruction on every clock tick. In other machines that don't use some of these techniques, you tend to see a less rhythmic behavior. You might get tick, 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 and all of a sudden you hit a complicated instruction that takes many clock cycles. And then instead of continuing execution, you stop while that instruction is executed. You have a hiccup in the pipeline.
Well, it's not only the Americans that are in the RISC business. Acorn have been evaluating their own 32-bit RISC processor called ARM, Acorn RISC Machine. The evaluation system has been around for some time, priced at about £4,500. But this is the first public showing of Acorn's development RISC machine. It's about 35 times faster than an IBM PC, and indeed it's 20 times faster than this BBC Master here, as you can see from this demonstration. In fact, at the moment they're both calculating a 3D graph based on sines and cosines. The Master is the small graph inset at the bottom right of your screen. If they could produce this RISC computer for, well, the cost of a master system, say £900, 20 times the speed for no extra cost, well, they'd have a very competitive machine. Alan Turing's definition of a computer was a universal machine which could undertake any task that could be represented in symbols, a machine that could be programmed. All the hardware we've seen so far fits that description, but this new machine for recognizing images can do only one task, so perhaps it's not a computer at all.
Now, you'll probably recognise most of these faces, and that's despite the fact that you're seeing each picture for only about a second. But getting a machine to recognise something as complex as a face is a major challenge. Now, each of these video images contained over 0.5 megabyte of information, and they were, of course, all the post-war British Prime Ministers. But the same face can look quite different, and we humans have no difficulty in knowing that this is the same person. But could a machine do the same thing?
Here is a machine from Brunel University that does recognise faces. It's called Wizard, and it's a pattern recogniser aimed mainly at industrial applications, like looking for faulty items on production lines. And it could be useful for something like security systems, as it can also recognise faces if it's taught them first. And I'm going to teach them my face. Leslie, would you like to operate it?
I'm going to teach them your face.
Oh, you're going to do it?
OK, are you sort of in position?
Yes, I am, and I can move my face around. Smile.
Right. Yes, keep your chin on the block, so to speak, Mac, but make all the usual silly expressions that you do. That's it.
Thank you.
The machine wants a fair old
It's
challenge.
got to be able to recognise me in any particular configuration of this ugly face.
That's right. I mean, the more information you give it by doing that, if you look up here on this bar graph, you can see Mac is actually going in there on line 4, that's the bottom line, and this indicator, which is zooming up 70%, 80% and 90%, shows the amount of information that Wizard is gathering about Mac's face, which will enable it to recognise it when it sees it again. It is 90% sure it's you, Mac, so you can now move.
Thank you. I'm sure it's me too. Well, we programmed some of the micro-live TV this afternoon, including Fred. Well, come on, Fred, let's see if we can separate you from all the other beauties in micro-live.
10 to 1, it says Robert Redford.
Oh, what?
Here we go. How's that?
Look at that picture. What a treat. Now listen, Fred, you're never going to get a new job with a face like that, you know. My goodness. But if we have a look over at the bar graph, Fred now is represented by number 3, and that's the indicator that's shooting way out to 90%. So in recognition mode, Wizard is very sure that that is Fred and no one else.
Let's see if we can fool it. Try with me with a pair of glasses on.
Oh, what's happening? What's happening? You've confused it completely.
How do I get to look like Mac?
Oh, it's not at all sure. What have you done? You've put Mac's glasses on, but no. Fred, you can't fool it. It's still absolutely sure it's you. Anywhere between 70 and 80% sure.
Right. Facial discrimination, I call it. There you go, Mac.
Thank you.
It's great. A presenter's lot, I think, actually, standing in front of a camera, hoping somebody's going to recognise you. So, how does it actually work? Well, it certainly doesn't learn all the pictures coming from the camera. The learning process takes a good 20 seconds, and in that time the video camera sends about 500 separate pictures. What it actually learns is patterns, and there are no transputers or exotic parallel processing devices involved, because, have a look at this. This is one of Wizard's memory boards, and as you can see, there are standard memory chips, but they're chips that are used in a very novel way. The picture from the camera is simplified into black and white, so each of the 50,000 pixels that make it up are either on or off. The system then divides the image into groups of 5 pixels scattered across the screen. Now, 5 pixels can form 32 different combinations, depending whether they're individually on or off. And each combination corresponds to one position or address in the small chunk of memory that you can see represented at the bottom of the screen. As Wizard takes different snapshots of Mac, it builds up a pattern in the memory block which represents his face as seen by these 5 pixels. But obviously 5 pixels are not enough to cope with the whole picture. There are 10,000 of these small memory blocks, each directly linked to a group of 5 pixels, and all learning in parallel and building up a unique impression of Mac. And all this using standard memory chips. You see, it's no coincidence that Wizard can discriminate between 8 faces at a time, and there are 8 blocks or 8 bands of chips on this board, and to each band there are 8 separate chips. So when a face comes along, the current image is compared with those in memory, and the nearest one wins. So, although Wizard might look as though it knows about eyes and noses and the shapes of mouths, it of course doesn't. It's just a machine for recognising patterns in the images it's being sent. And to do this, it uses a network of memory, which is more like the way that our own brains work. In fact, one of the people who developed Wizard, Professor Igor Alexander, reckons that eventually it should be possible to produce something equivalent to a human brain. And at the present rate of progress, he estimates that it'll take about 1 million years. Well, that's it from Microfile. Remember, notes to cover the whole series are available from Broadcasting Support Services, or BSS, PO Box 7, London W3 6XJ. That's Broadcasting Support Services, or BSS, PO Box 7, London W3 6XJ. In the meantime, it's just
Goodbye.
bye-bye.